Thank you all for being here. This is a closing talk of this conference. Me and my colleague Jasper, we will be talking about ODINA. And ODINA is a grid planning tool that we have developed within TenneT in the Netherlands. And in this talk, we're going to talk a little bit about why we have developed it and what we're doing with it, and also what our future plans are with it. So first, let's introduce ourselves. I'm talking, so I'll start with myself. My name is Edwin Derks. I'm a domain architect in the strategic asset management domain. And my job is essentially to put people, processes, data, and tools together and make it all work together. And for this talk, important, ODINA is one of these tools. Jasper.
Yeah, and the ODINA team is there, 5 people, 4 really smart people and me. And we're trying to build this toolbox for really fast grid analysis. We want to look into the toolbox itself, into the basic concept behind the toolbox, and then we'll continue about how that we want to get that toolbox running in an actual application in the cloud, but that is Edwin's part. So if we start about what's happening in the Netherlands, it's a well-known picture. We have a lot of congestions in the network due to a sharply increasing demand. So if you look at supply or demand capacity, the Netherlands is turning red, so we don't have any capacity left for connecting new customers. The list of new customers is endless, and we need to do something about it. Meaning that we need to do a lot of grid analysis in order to improve this. So then the second question is like, that's an open question here, well known. So what is going on here? So TSOs are creating software. So why are we programming? And if you look at the past, I mean, in the 70s and 90s, all the TSOs were programming. They all made their own software because there was nothing off the shelf. And then in the 90s and zeros, you saw these well-known software, monolithic software coming on. So they took it out of our hands. And now we discovered that these softwares is not any longer up to the job. And we decided, as all the DSOs and all the TSOs, we decided that we have to create software again because we couldn't buy it. The reason for that is, of course, the sharp growth in grid analysis requirements, huge increase in investment, significantly more connection requests, and the whole world is changing. We're going from a megawatt world into a gigawatt world, and that means that we cannot do network planning with a few thousand load flows. We have to do billions of load flows now, and the software that we can buy is just not fast enough. So the first thing that we were thinking about is, okay, so if we want to create a new package, we need a grid model. So we were thinking about this a few months because we wanted a grid model that was not only very versatile, but also very fast and would connect to SIMGMS very easily. Now, if you want to have a fast network model for fast calculations, you want to have a simple model, like a simple node edge model. But if you want to do more detailed analysis, you want to have a detailed model. So what we thought about is that we basically have a node and edge model, but by forward pointing objects, we can enhance it and we can just add more data whenever we want without actually having to change the original node edge model. So that is stable. We have a stable node edge model. Any data that we want, any data that we additional need, we will add it to it by forward pointing. And we will never point back because then we need to change the node and edge model, which we don't want to do. And this model is tailored to speed and interoperability. So that's what we want to do. Now, the problem that we have actually is that if you compare this so this should be an open source project. That's what we're targeting. We want to go open source with it. And if you compare open source with classical off-the-shelf, the off-the-shelf software is like public transport. Yeah, it starts where you not are, and it goes to where you don't want to be, and it doesn't offer you the service that you want. Yeah, that's the problem with off-the-shelf software. And we have been dealing with the first two problems for years. Yeah? We have been the first mile and the last mile you have to write scripts in order to make the software, this proprietary software, work in your company. And that is now the problem that we have. Yeah, we have to change this. We have to rewrite basically all the applications that we have for planning and operation. And if you zoom into our solution, we want to have high speed. We want to have, I mean, if you talk about, if you compare it with trains or public transport, we don't need a bullet train, we need a rocket train. We need to really need to do billions of load flows. So we need to be really, really fast. And basically what we need to do is, we have a grid, the grid transports power. We have incoming power, like generators, power plants, the wind parks, whatever, pushing power into the grid. And of course we have consumers taking power from the grid. And then we have adjustments and events that can happen that change the grid, like phase shifters, HVDCs, planned and unplanned outages, switching topology adjustments, everything that happens in the grid. And if we want to do high-speed calculations, then we need to be able to calculate with all these possible changes in the grid. Because what we want to do is we want to calculate the load flow, detect congestions, and then do remedial actions. So our idea was to use linear load flow, because linear load flow is really, really fast, much faster than AC, and it is good enough for planning purposes. You make a linearization error, 5 to 10% maximum, and that is okay. But the problem is, we have PTDFs, well-known PTDFs, we have LODFs, or linear outage distribution factors, of power transfer distribution factors. So these are factors that you can use for linear calculations, but they don't cover everything. They don't cover planned and unplanned outages, they don't cover switching, topology, and other changes. So we started starting a scientific project in thinking like we need to cover all possible changes. Now PTDF is well known, LODF is well known, but we needed to develop multiple outage distribution factors, which that was not available. We couldn't find it anywhere. We needed PSDFs. At that time that we developed it, it was not available yet, so we developed it. And the last part, the last closing stone of our toolbox was the bus merge distribution factor and the bus split distribution factor, which allows us to linearize topological changes in the network model. And we saw today a presentation where this is actually being used by 50 Hertz to get really fast topological changes and being able to analyze them. This together makes the brain of ODINA. And as you see, on the good brain, you don't have any hair, like me. So this is the brain of ODINA. This is the basics behind the toolbox. I think the unique selling point that we have is this blazingly fast linear optimization, linear calculations and linear optimizations. And that brings me to what we mean by realistic precision. So it's really fast linear load flows. But why do we call it linear precision? Because we know that we make a linearization error. But these calculations deliver you exactly the same results as when you would do a DC calculation in, for instance, Power Factory. Power Factory is for us still the golden standard. So what we do is we make some changes, some adjustments, we put some incoming power, outgoing power, we calculate the load flow, then we export exactly that situation to Power Factory, calculate the DC load flow in Power Factory, and compare the results. And for us, our goal is to get exactly the same results up to 4 decimals. And that's important, because if we go to operators and or managers and we want to gain trust, then the first decimal doesn't give you the trust, give them the trust that the results are correct. But the 4th decimal does. And that's why we focused on getting exactly the same results. So that's what we call realistic precision. There are no approximations, no network reductions. We have realistic contingencies, and the results are exactly the same as what you would get from Power Factory or any other off-the-shelf software. And we have full specifications because we cover any change in the network model. So that's nice. So we have super fast, full spec calculations, realistic precision. We are building, extending the network, the toolbox at this moment. So we have detailed calculations, so AC load flows in full precision. And of course we can, because we have a linear load flow, we can do very fast optimal optimizations for congestion management, very flexible. So any optimization, phase shifters, HVDCs, flexibility, we can deal with. So that's the shortest introduction in ODINA that I ever gave in exactly 10 minutes, I think.
Then I will give the software introduction that I will have ever gave. So I'll take over for now. Yeah, so it's nice now that Jasper and his team created this library, and you can run calculations with it. Perfect. But you cannot all work on Jasper's laptop, and yeah, we need to bring it to the people. And that's where software development comes in. So we are kind of productizing ODINA with all its components for certain purposes into all products. And one of those products I'm going to talk about how to show what our approach is in that regard. But first, let's go a little bit back to why we do this. Jasper already mentioned there is a lot of congestion in the Netherlands, you can say that. And it manifests itself in news items like this in the province of Utrecht, where congestion is being sometimes handled at the end user side instead of in the grid. And for me, the big change will be if we can calculate fast enough and parallelize these calculations enough that we can do a lot of more congestion studies and change the grid accordingly. These kind of news items should disappear and should hopefully even turn into praises of the government saying, oh, TenneT has full control over congestion now. So that's kind of the end game we're playing. But to get there, we need to work on this productization of ODINA. For the historical purposes, just to show, congestion studies was done or is done on a net strategist laptop using a lot of input data, often shipped with Excel. The world is built on Excel, right? So Excel is also a big factor here. We're using Power Factory for grid models and for the calculations. Now, out comes a result, and it can be used in a congestion study, and that can be used to advise on whether or not to expand the grid somewhere. But the studies can take days, weeks, sometimes even months to conclude, and if the problem is really intense, then you can lose opportunities to change the grid, and the customers can be waiting, and then you get these self-managed congestion solutions, and that's what we want to prevent. So with more congestion studies done faster and in parallel, then we hope we can better service the grid by being more flexible from the TenneT side. So that's why ODINA is going to play a big role in changing things around. But again, scalability problem is on the laptop because you cannot just copy your laptop and do it's not how it works nowadays. We need something better. So this whole thing, we need to modernize in something that is scalable, fast, data intensive, and compute intensive. Now, who knows? Who could have guessed? The cloud is, of course, where we want to run the calculation with ODINA. We still will be using for the foreseeable future Power Factory, at least for the grid models, because that's still the steady state of models that we use for the calculations. We're going to put the pieces of the ODINA toolbox that we want to use in there, somewhere, somehow, in an application that we are going to call ACAM. It is the Automated Congestion Assessment Module. I'm going to talk a little bit about that in the next slide. And we want to handle the data properly. So we essentially want to de-Excelify our ecosystem and do data processing, calculation, and software properly. Now, in comes the world of software development. I'm not going to give a big introduction and deep dive into software development. I can be talking for days, and I don't want to keep you here for another few days. But we are building microservices. Who has heard of microservices? Yeah, don't be ashamed. Yeah, this is the buzzword of everything. No, but all jokes aside, we have a cloud environment, so we want to have software that's built to make optimal use of the cloud environment with development pipelines and build teams, DevOps teams to do it in the industry standard way. So nothing specific for TenneT, it's just, yeah, as standard as possible. Don't make it more complicated than it has to be. Now, putting things together then, with this cloud infrastructure, and this is a high-over picture of what ACAM would look like then. The cloud infrastructure facilitating ACAM as an application consisting of multiple functional components, in this case called ACA and GAM. And ACA will be the Java-based standard enterprise application with an Angular front-end presented to the user. Because we don't want our end users, our net strategists, being writing Python scripts all day. We want to present them a nice, workable graphical user interface where they can prepare the net congestion studies and also properly handle the results. And also this connects to the inside and outside world, so all data sources from TenneT inside and from the DSOs from external can be set up like this. So this application has a big part to play. But maybe for this talk better and more important, the grid analysis module will be the wrapper around the ODINA code that actually runs in the cloud in containers and is scalable. So this whole infrastructure, the whole thing that we are putting up within TenneT for actually running Jasper's lines of code in Python is to make sure that we can in the end battle congestion with a scalable IT that also directly supports the way of working of the end users. So this is where it all is going to be put together, and hopefully we will be seeing the results very soon in the Netherlands. But we are here on an open source conference, and we are in very deep conversations with the LF Energy Foundation. We want to open source ODINA to this foundation because we want to give back to the community that we also use for open source. And we are looking into how we can do that. Now, open sourcing ODINA, because the O is for open in ODINA, Open Development Initiative. For the team of Jasper, it's a no-brainer, but for TenneT it's the first time, so we are slowly but surely getting to the end that all managers say, okay, this can be done, and we support it. And hopefully will result, when we are through this, in more open source contributions in the future. That's also why we are here on this conference, interacting with a lot of you, having a good conversation, and we are willing to collaborate more and more to make sure that TenneT is also going to be playing a big part in this ecosystem where we're all in, and not being a silo and a silent partner on the LF Energy until now. Questions? Do you want to add anything, Jasper? Or
I understood everything.
Okay. Phew.
Yes. By distance.
Thank you. Kevin from Expo, Switzerland. In your slide 7, you mentioned realistic congestion. Is there also an unrealistic congestion? So what can you demystify the term realistic here? Realistic contingencies here. What do you mean by realistic?
Realistic. So the realistic means that the network model that we have, I mean we use linear load flows, but that's it. All the rest that we use, all the data that we use is realistic. And for instance, contingencies, normally contingencies are by outages. So they say like I have an outage on a line, but lines do not outage by themselves. You have a fault on a line, and then you have to actually analyze your network model. You have to say like, what is the effect of the, you need to do a failure effect analysis. And that is also what we do. So we have realistic contingencies where we actually do this failure effect analysis and take out the parts that actually are affected by this fault. So we have faults in the network and not outages for unplanned outages. we're analyzing the effect of the fault and not just single outages. Yeah, like Power Factory does. Yeah. So that is the realism that we have there, and for the rest we don't make any approximation. It's just we do a linear load flow, but that's it. The rest is realistic. That's why we call it realistic precision. Oh, sorry. Yeah, you want it?
In the previous presentation on topology optimization from 50 Hertz, they mentioned they are collaborating with TenneT. Is this also integrated into ODINA?
No, it's the other way around. Yeah, so we developed this bus split and bus merge distribution factors, and I think we delivered code to them, but they put it in their system. I think they rewrote the code. I'm not sure if they actually took the code, but they took the principle and the formulas that we developed.
They are using this DNGF and DSDF.
Yeah. It's like we also developed based on these. We also developed the flow decomposition the calculation, the FLD calculation, and the same way Power Factory read our papers. We publishing everything that we do. So the read our papers. They asked us some questions, and then 1 year later, suddenly Power Factory had FLD, which looked exactly the same. Even the name of the parameters are the same as what we had. So they just copied the ID without actually using code. So this is a kind of, is this still open source? It's more like open IDs that they, yeah. But it's the same thing. It would be nice if they would have thanked us, but they didn't do that. Or percentage of the profit would also be nice. More questions?
Yeah, I have another question. I don't know if you can come back to the data flow representation you had at the very beginning. Well, first of all, thank you for the presentation and congrats. It looks
this one?
really amazing. No, when you show the CSV and yeah. So at the very beginning, yeah, exactly. In this slide, you were mentioning that it's close to SIM CGMS. I don't know, what do you refer with that, or how close it is?
Well,
that's the first question.
It's so close that we don't have any problems we don't have a CGMS importer yet. We have half one because we had to stop and have to do some other stuff, but we will have a CGMS importer, and we know there will be no problems in actually parsing the data to our model, because our model looks already more or less like what CGMS does in the same way. So it's not the same, but it looks the same. So we don't need to throw away data, or we don't need to convert data. We basically can import it as it is and project it onto our model.
Yeah, but then talking about scalability, do you foresee that this tool is used by someone for cross region purposes? That is, do you expect that you get some data from a DSO outside of the Netherlands? And in this case, I guess that you are expecting that they understand your information model that you define, I guess, in the columns of this CSV?
No. This model is completely, basically hidden inside ODINA. So we don't expect this. Nobody should use our ODINA model. This model is just internal to our toolbox.
When you receive the data, in which...
By importing well-known standard formats like CGMS, or maybe in the future other. We can also import. We import at the moment. We import Power Factory models, but we do it through the API. So we just connect to Power Factory and just take all the data that we need. But we can also import UCTE format, the PSSE. We can also import from PSSE. Mm-hmm. So we're not suggesting that the ODINA data model should be used as an exchange model. It's for internal use only. So we don't actually want the users to know that we have this model. It's just completely hidden.
Sure, but at the same time, you're expecting that someone is sending a model in Power Factory format. Yep. I was quite excited in seeing this because, okay, then I understood, but maybe they are having a CGMS or SIM exporter, and you're having a SIM no-code profiles exporter to export all these remedial action, topological actions that you are talking about. I don't know if this is something you would consider to expand in the future, because yeah, that's where the direction of standardization is going. So I understand that at the moment you don't have an importer of scene CGMES, you don't have an exporter of scene CGMES or any other scene-based profiles. So my question is, do you expect to have that in the future?
Yeah, sure.
All right.
Yeah,
Yes,
so we want to be, interoperability is a big thing. So we want to be as interoperable as possible. So being able to import, export. We are able to, at the moment, using Power Factory because that is the network model data that we have in TenneT. But we also export to Power Factory. So we can import a model, we do calculations, and then for specific hours, we export those situations so they can be then further analyzed with short circuit analysis or harmonics or dynamics or whatever. So that is what we are doing at the moment. But the future, probably, we will change that to CGMS and we will just export the results also in CGMS. Yeah.
I actually have to say that wise decision because Power Factory actually has a CGMS exporter, so you are actually exporting CGMS through Power Factory.
But that again is a problem because we want to add new fields to new objects to CGMS because we want to export more. We have data within TenneT that is not yet in the standard CGMS, so we want to add that. And yeah, the Power Factory does not have that, so we will never be able to export CGMS through Power Factory. That doesn't work. It's just too fixed. We cannot do that. So we will build this exporter soon, and then we will be able to use CGMS.
Great, thank you.
You're welcome. Any more?
Just last question, maybe from my side. Okay, there is another one. Okay, before the last one. I saw that there is the linear power flow that how it is connected to the Power Factory, to Dixisland. How?
We only use the network model. So Power Factory for us is nothing more than a network model editor. That's what we. So there's a network model there. We open the API, we take all the objects, parse them to our model, do all the calculations in ODINA, and only the results are then exported back to Power Factory.
Okay, great, thank you.
Yeah.
Maybe this one.
Yeah, thanks. Yeah, it's the last presentation, so we have all the time of the world. So that's.
I was wondering what kind of optimization methods you include.
That's a good question, because now I have to admit that we are using very simple linear programming. So linear programming, we also have quadratic programming for some other problems, but we're using basic linear programming. The nice thing about that is that you can leave everything the same and only change the right side of your linear problem. That means that we can actually build this whole linear program, this whole linear problem as a big matrix, which takes a little bit of time. But then we can quickly go through many hours and just only change the right side of that problem and solve it again, which gives us a really fast optimization. Because we can calculate, in the linear load flow, you can calculate load flows for multiple hours, n minus k, in one single matrix multiplication. So we have a big matrix, two of them, you multiply them, and then what you get is the load flow for all the hours in one single action. That's what we do. So we do a year-round load flow in 20 seconds on a laptop. But you cannot do that with optimization. You have to select all the hours with congestion, and then you have to optimize those hours one by one. We cannot do all hours at the same time. Theoretically, you could do that, but then you need a lot of memory and a good solver. So we have to do them one by one. But by using this trick of only updating the right side, it's still fast enough to do a few hundred or a few thousand optimizations for 1 year. So that's why we have basic linear programming. Yeah. Any more questions?
Thank you for the presentation, and exciting to hear you're looking to open source this. What are the things you hope to gain or from open sourcing the project?
Yeah, we want to sit back and let you do the work, of course. No.
Yeah, so are you looking for new features or integration with other tooling, testing, working together with other DSO, TSOs?
Yeah, that's the whole package that we want. We want to join the open source community. There's one thing that is still in the back of my mind is that we see now that we have there are different network analysis packages now in open source. We saw at least 3 of them today and yesterday. I don't know where we are going. If we add another one and maybe next year another one, that doesn't solve the problem. Yeah, it would be much better to have one good package that combines all the good stuff of maybe the various packages. I don't know how that will go, but basically we're open for that, for consolidation, and come up with one amazing open source network analysis package. Maybe that would be the end of it, but the start would be to go open source, to let everybody know what we have, let people use our software, use our methods, and then, yeah, the best one wins. Yeah, that's the way it goes, I think.
Okay, cool. Thank you.
Okay. No more questions. We go home. Wonderful. Thank you very much.